Hello, everyone. This is a re-recording of the Introduction to Quantum Computing and Qiskit. The earlier recording for the day was lost, unfortunately, but we are going to do it again, and I'm excited. By the end of this, we're going to be able to explain why quantum computing matters, be able to compare what a bit is versus a qubit, describe superposition, entanglement, and interference, and recognize a quantum circuit in Qiskit. This is a very high-level overview, just getting us familiar with the terms that we'll be using. We're going to use a lot of analogies, and we're going to move into the Hello Quantum world from IBM Quantum. We're going to have more sessions in the coming days where we dive deeper into how circuits work, how qubits works, gates, Bell states, the whole 9 yards. However, today is just a gentle introduction. So, some problems are so hard that classical computers cannot solve them. And I don't mean today's classical computers. I mean there does not exist a classical computer that can solve these. To simulate a caffeine molecule, you need 10 to the 160 classical states. A truly mind-boggling number of states. If you want to optimize a supply chain with 100 cities that are all connected to each other, that's 100 factorial routes. That's more than there are atoms on Earth. So even if you could represent a bit with every atom on Earth in a classical computer, okay, you couldn't recreate this. You couldn't represent the entire system at one time. So training AI on quantum data, we also see that classical models break whenever we are dealing with quantum effects trying to represent with classical physics. So what we are looking for here is a new computing paradigm that allows us to tackle these huge and very difficult problems, where we have these huge search spaces to try to represent. Quantum computing allows us to do that through the methods of superposition, entanglement, and interference. So, supercomputers use bits. Okay, even the best high-performance computer uses zeros and ones. All right, to simulate 300 atoms, you would need more memory than atoms in the universe. You know, with all their energy states of their orbitals and how they interact with one another. So it is impossible for us to make a computer that can, in real time, simulate 300 atoms. And 300 atoms is a microscopically small amount of matter. Now, we can extrapolate from smaller simulations and things like that, but we run into pretty quickly, whenever we look around the world around us, a set of problems that are impossible for us to truly compute. So with classical scaling, we have exponential cost, but with quantum scaling, we're hoping for exponential power. Okay? However, a quantum computer is not going to replace your laptop. Quantum works with classical. These systems hand things back and forth to each other. Quantum computers are expensive to run. They require repeated shots. They require typically cooling to ranges of like 10 millikelvin, almost absolute zero. So we need to hand back and forth between quantum computers and classical computers, and allow classical computers to handle linear processing of tasks and the things that we've spent the last almost 100 years optimizing them for. For quantum computers, whenever we encounter these very, very large search spaces where we need to calculate a vast number of possibilities, that's where quantum computers come in. But another aspect of this is that these are going to be intricately tied into each other. The things that operate these quantum computers are classical computers. For the hardware, the manipulation, whatever pulses are required to complete your commands to the quantum computer, those are regulated with classical computer. These are going to work together. Let's talk about bits versus qubits. A qubit is simply the quantum version of a bit. So where a bit is in 0 or 1, it represents one state. Think of it as n coins sitting on the table. Okay, that at any one time, you only have one state. Coin 1 is heads, coin 2 is tails, coin 3 is heads, coin 4 is heads. That's one state. Whereas qubits can exist as 0, 1, or a combination of both. And by being able to represent those combinations, we can represent 2 to the n states with n coins. You have n coins spinning in the air. They're neither heads nor tails until we measure them. So with 3 qubits, we can represent 8 states simultaneously. And with 300 qubits, we can represent more states than there are atoms in the universe. This is the power we're hoping to leverage with quantum computing. So, superposition, neither 0 nor 1. It is in some combination between them. All right, it is both until that coin lands. So a qubit held in superposition holds 0 and 1 at the same time, but whenever we measure it, we catch the coin out of the air or it hits the ground, it collapses to be either heads or tails. That's what happens. So, if it's in equal superposition, it's equally 0 and equally 1. 50% of the times whenever we measure it, it'll be heads, and 50% of the time it will be tails. Entanglement is a mechanism whereby we connect 2 qubits. We entangle them together such that whenever we flip them, we set it such that if one comes up heads, the other one will come up tails. Okay, and we can apply this entanglement and they instantly correspond with one another in the absence of noise. Now with interference, we are allowed that we have these qubits in superposition. They're representing all of our 2 to the n states, but we can provide negative interference towards the results that we don't want or are not looking for. We can provide positive interference towards the results that we are looking for. So we're able to use interference to simultaneously adjust the states of the quantum circuit. I've said quantum circuit a few times. And so this is an illustration of a quantum circuit. We have qubit 0, we have qubit 1, we have some classical bits down here. We apply this H gate, this funny one with the plus sign, and we get an output. Now, whenever I say quantum circuit, we are not building a circuit like a circuit board in a classical computer. A quantum circuit is an abstraction. This abstraction allows us to define the quantum system that we want to conduct the calculation that we want to, and then we use the Qiskit programming library to translate that into the hardware code. The actual hardware has some qubits next to each other, some not, some gates that it can use, some not, and Qiskit is the go-between between our abstract quantum circuits that we're using here and the actual hardware. But Qiskit's not that hard to learn. It's a large library. There's a lot of functionality there to learn how to do effectively, but it is just a Python library. You run pip install Qiskit, and then in your normal Python format, you develop a quantum circuit, you put a gate on qubit 0, you entangle qubits 0 and 1, and it works. Additionally, you can deploy your circuit to real hardware if it's large and complicated, or if it's a smaller circuit or you're prototyping, you can simulate it on your laptop or your home computer. A couple caveats. I've used some simplified analogies here. The coin flips and paths canceling each other out. But at the same time, as you go deeper, it'll get deeper. But you don't need to be a physicist or a mathematician to be a quantum programmer. It's more about understanding how algorithms work and how data works than it is about understanding the quantum mechanics. Quantum computing, however, is also still young. Oftentimes I relate it to like classical computing in the 60s. They're very big, they take up an entire room, and they can't hold a lot of data. But we have the advantage of everything that we've learned from classical computing, and the space is rapidly developing. We are learning what kind of problems we can solve with quantum computing, and I'm pretty excited about where it's going to go. Some key takeaways is that quantum computers are being designed to solve impossible problems for classical computers. The key principles for quantum computing are superposition, entanglement, and interference. And Qiskit is the programming library from IBM that relates these abstract quantum circuits that we've talked about to the actual quantum computers. A lot of times, newcomers to quantum computing become fixated on how does superposition or entanglement or interference work. There are aspects of that you can understand more deeply. However, there's a lot of these things that once you dive deep enough, we just don't really know. But we do know they work. These have been experimentally validated. We have been able to show that entanglement works, that superposition works, and that these qubits can interfere with each other. So it may be a thing of that we're not exactly sure why entanglement happens, but we do know that it happens. I'm about to walk us through a quantum hello world. It's a walkthrough of deploying your first quantum program. It's from IBM Quantum. It's a little bit aggressive on all the things that it shows, but it does walk you through it, and I will be available on Discord if you guys have any questions about how to do that. And so let's dive in. All right, so I've taken this from IBM Quantum. It's the Lab 0 of their Qiskit Global Summer School that I attended this summer. And the goal of this is a basic introduction to how Qiskit works. So the first thing we have to do is install the libraries that run Qiskit. So we have Qiskit, which are the things that we use to build our quantum circuits. We have the Qiskit IBM runtime. This is the translator. This takes our circuits and deploys it to the real hardware. There's lots of other things that are involved in this. And then Qiskit Error is our simulation platform. Qiskit Error allows us to simulate these circuits instead of running them on real hardware. Oftentimes for these kinds of tests or whenever we're prototyping our algorithms, we'll simulate them first instead of using expensive quantum computation time, which you get 10 minutes a month free, but at the same time, we shouldn't waste not, want not. But we can simulate to prototype that our algorithms are working the way that we want before we deploy them to real hardware. All right, we import these. Now, where do I use Qiskit? Personally, I do most of my work on the cloud. I use environments like Colab or Kaggle or Google Cloud or GitHub.com, and I run my code in the browser. I switch between multiple devices a day. It works well for me. If you have a personal environment that you like to work in, there are instructions below on how to install Qiskit on your personal machine and how to make that work with Anaconda or VS Code. I like the Colab running because I do my pip install, I import, and I'm off to the races. Okay. However, you will need an IBM Quantum Platform cloud account. You will create your sign-in and your password. There are instructions right here that describe how to set up your cloud account. Sometimes it will ask you for credit card information. You do not need to use more than your 10 minutes a month. They won't charge you monthly or anything like that, but you will have to watch that you don't use more than your 10 minutes. Now, once you've created your IBM Cloud account, you'll be able to access your API key and your CRN. These are what allow you to deploy your algorithms to the quantum hardware. So, you'll be able to paste in your API key and your CRN into notebooks like this to be able to use the quantum computers. And then from here, there's a series of imports, and we gently walk you through how to create a quantum circuit, add gates, how to draw your circuits, and it's a nice tutorial. And then we allow you to do it, where you write the code. I think you guys get that. We show you some transpilation steps with our preset pass manager. And that's it. I am here for you if you need me. Please reach out to me on Discord and be more than happy to help. All right. Thank you.